How's it going, everybody? We are now going to get into a section setting up for inferential statistics. We're going to be getting into probability, and the next 4 topics, including this one, so probability plus the next 3, are all going to be preparing us for inferential statistics. So what we're going to focus on today about probability is the rules of probability, and this is going to give you some practice with the concept of probability, how to do some easy probability calculations, and primarily getting you familiar with probability thinking or probabilistic thinking that's essential for understanding inferential statistics. So let's go ahead and get into probability. And what I want to do before we get into some specific things is give a fun little example of probability to kind of get your minds thinking in the right way. So this is a fun little probability thought experiment called the Monty Hall problem. Okay, so I'm going to read through the rules here and then just follow along to try and to understand the setup here. So imagine that you're on a game show and you're given the choice of 3 doors. Now, you're told that behind one door is a car and behind the others are goats. Now, the car and the goats were placed randomly behind the doors before the show. Okay, now here are the rules for you as the contestant. After you have chosen a door, the game show host, whose name is Monty Hall, who knows what is behind the doors, he's going to open one of the 2 remaining doors, and the door he opens must have a goat behind it. If both remaining doors have goats behind them, he chooses one randomly in his mind. That's what he's doing there. So you choose a door, and he's going to open one of the other doors, showing you a goat. Now, after Monty Hall opens a door with a goat, he will ask you to decide whether you want to stay with your first choice or to switch to the last remaining door. So you want to stay with the door that you chose at first, or do you want to switch to the other door that is left? So follow this scenario, for example. Imagine that you chose door 1. And the host opens door 3, revealing the goat. He then asks you, do you want to switch to door number 2? So your question to think about is it your advantage? What gives you the better probability of winning the car? Staying with door number 1 that you initially chose, or switching to door number 2? Now, if your thought is to stay, then that would actually be disadvantageous to you. It is actually in your advantage to switch your choice, always. You will win more of the time. In fact, 2/3 of the time that you play this game, you will win if you switch your choice. Now, many people will think like, but how is it that my advantage is better? When I face between door 1 and door 2, it's a 50-50 chance. And that is where we go wrong in thinking about the probability of this game. Remember that we started out with 3 doors. So the probability of picking the car was a 1/3 chance. That probability was locked in the minute that the doors were closed and and everything was mixed up randomly and we make our choice. So when you are faced with door 1 and door 2, it's still a 1/3 chance that your choice of door 1 would have been the winner. Now, if you switch your choice, it's almost as if like you had chose 2 doors at the very beginning. It's almost like your second choice was just delayed until after the host revealed one of the doors with the goats. But imagine that you were able to choose 2 out of the 3 doors right at the beginning. And let's say you chose door 1 and door 2. Well, now you have a 2/3 chance of picking the door with the car behind it because you picked 2 out of the 3 possibilities. And that is essentially what's happening here. Now, most people don't think about that. They just see 2 doors in front of them at the very end, and they think, oh, it's 50-50, so why not just stay with my choice? Or some people would say, well, why not switch? And even people who switch, they would win more of the time, but they might not even realize why. Because when you switch your choice, you're essentially picking a second door, which increases your chances from 1/3 to 2/3. Now, this next slide gives you a little illustration of how this probability works out. You can pause the video and kind of work your way through this to see if this is clicking with you. And this is using like a diamond under the cup. So essentially anything could be used for this. Take an object and hide it under 3 things and move them around, and then have somebody do this with you and have them pick one and then do the other, track their choice. And you would see that if they switch more, they would win 2/3 of the time than if they stayed. Okay. Now, why do I show you this? Because even after I explain this, you still might be pretty confused. In fact, you still might feel like this kid in this little picture here, right? And the reason this is confusing to us, even though I've explained it, and even though you're maybe paused and look through that picture there, you're still confused. And the reason that I give this demonstration is to illustrate that we're not so good at thinking of probabilities, right? You can follow this link on the slides here for a more detailed explanation. Maybe that'll break it down, but the Monty Hall is not something that you're going to be evaluated on. That was all to demonstrate that we need to get better at thinking about probabilities, especially since probabilities underlie the fundamental usage of inferential statistics. So now let's get into some specific rules of probability and how we can actually calculate some probabilities with the goal of getting better at thinking about probabilities. So what I want to do here is set up some basics of probabilities, and we're going to be using a 52 deck playing cards to use. It's a classic example for probabilities, and that's what we're going to use for a few examples here. Now, how do you calculate a probability? Well, here is the very simple equation. You take the total number of successes over the total number of events. So let me give you an example with this. So what is the probability of picking an ace? Well, how many aces are there in a deck? 4 aces. How many cards total in a deck? 52, right? So you would have, the probability is how you would win, quote unquote, if you picked an ace. There's 4 aces, so that's the number of successful draws that you have available out of a total amount of 52 cards. So you take 4 out of 52, you take the division of that, and the result is a 0.077. That's the probability, okay? And in fact, every card has the same probability of being picked because there is 4 of a kind of every kind of card, right? So I'm just going to replace that previous image with this one here, where we just see the probability is 0.077 for every card that we have there. So it's 4 of every card. So same probability for every card being picked. Now, what is the probability of getting a 10, a jack, a queen, or a king? Okay. Well, here's what we would do. We know that we have a 4 out of 52 chance of drawing a 10, and 4 out of 52 drawing a jack, and same for queen, and same for king. So really, if I draw one card out of the deck and I want it to be a 10, jack, queen, or king, I have a 4 plus 4 plus 4 plus 4 chance out of 52 cards of picking one of those 4 out of the deck. So really, I have a 16 chance. I have 16 chances because there are 4 tens, 4 jacks, 4 queens, 4 kings. So 16 cards meet the criteria for me picking one of those face cards out, face cards in the 10 card. So the probability is 16 out of 52, which is 0.308. So I have about almost a third chance of drawing a 10, a jack, a queen, or a king. Another way you could do this is just take the probability decimal-wise of picking one of those 4 cards and add them together, and you get the same decimal. So it works out in the same way. I want to show you both ways, the fraction and adding the decimal, so you can see how they both get to the same result. Here's another one. What is the probability of drawing a 2, and then after putting the 2 back into the deck, drawing one more card, and then also getting a 3. So from the top of the deck, you draw a card and it's a 2. What's the probability of drawing that? And then putting it back into the deck, somewhere in the middle, and then drawing the next card on top, and that card being a 3. Well, what you would want to do is you want to take the probabilities and you multiply them together, right? You have a 4 out of 52 chance of drawing a 2, and then also a 4 out of 52 chance of drawing a 3. So you're going to multiply those together, or you can multiply the fractions together. What's easier is to multiply the decimals together, and then you get 0.006. That is a very low probability of drawing cards of those exact kinds, one after another. Very, very low that would happen that specifically. Now, one more. What is the probability of getting blackjack? Common game, gambling game with cards is called blackjack or 21, where the goal is to get as close to the number 21 by adding up the cards that you draw from the deck. So if you were to draw a 10 and an ace is worth 11, or an ace is worth 1 or 11 points in blackjack. So if you draw a 10 and an ace, then you get 21 right off the bat. Usually when you draw that, you win immediately. So what's the probability of getting that very highly valued combination of cards? Well, let's look at what would be the probability of drawing a 10 or a face. We already calculated this probability earlier, right? We just take the probability of a 10, jack, queen, and king, and then you add them together. So the probability of that is 0.308. Now, what's the probability of drawing an ace? Well, we know that we have 4 aces possible out of the total amount of cards, but notice that when I draw you your first card, and it could be a 10, a jack, a queen, or a king, I'm not putting that card back in the deck, right? Because we're going to draw 2 cards total. So now that the 1 card has been removed, the total amount of events has been decreased. So it's not 4 out of 52 probability for drawing an ace, it's 4 out of 51. So now it's 0.078. And if I want to know what's the probability of drawing these cards successively, first drawing a 10 or face card and then drawing an ace, well, we're going to do what we just did previously, like drawing a 2 and then a 3. We're going to multiply these probabilities together. And so ultimately, you get a probability of 0.024, which is the probability of drawing blackjack. Very unlikely that you would get blackjack on your first 2 draws out of the deck. So these are some examples of calculating probabilities using cards. Let me give another one that uses dice. So these probabilities are a little smaller, a little easier to work with. So let's kind of use some examples with this. So what is the probability of rolling a 1 using a single 6-sided dice? Well, it would be 1 out of 6, right? There's 6 sides to a dice. Each side has its own number. There's only one side with the number 1. So it'd be 1 out of 6 sides, you get a 1. So it would 0.166, 1 divided by 6. Now, what is the probability of rolling either a 1 or a 2 with a 6-sided dice? Well, the probability of rolling a 1 is 1 out of 6. And the probability of rolling a 2 is 1 out of 6. And when we want to know what's the probability of this or that, we add the probabilities together. So we get a 0.332 chance. You have pretty much a third chance of rolling a 1 or a 2. Now, what is the probability of rolling 2 1s using 2 6-sided dice? Right, so I've got to get a 1 on one dice and a 1 on the other dice. Well, I know that rolling a 1 on one dice is 1 out of 6, and I know that rolling a 1 on a second dice is 1 out of 6. But if I want to get 1s together, then I would have to multiply them. It's the same concept of drawing 2 cards out of the deck of specific kinds, drawing blackjack, for example, right? So I've got to multiply these probabilities together, and I get 0.028. You got about the same chance of rolling 2 1s as you do of drawing blackjack from a deck of cards, based on the probability there, 0.028. So this is some initial things of working with probability. So let me give you some specific rules. Like, why is it that we add and multiply when I've shown you here? I'm going to explain that for you. So the first thing I want you to know about a probability is that the probability, as it's calculated, will always fall between 0 and 1. Now, 0 indicates that the event will not occur. It is like not possible for it to occur. 1 is that the event must occur. It could not have happened. So in real life, probabilities will fall between 0 and 1, but they will rarely ever be 0 or 1. And it might be safe to say they'll never be 0 or 1, because everything in the world has some likelihood of happening, either greater or lesser. But it will, it's not that it will never happen or it must happen. It's somewhere in between. So that's the first thing to know, that probability should always fall between 0 and 1, and always be a decimal of some sort. Now, here's the first rule of probability I want you to know. This is the term called mutually exclusive. It's where the occurrence of one thing means that the occurrence of something else could not have happened. Okay, so if one thing happens, it means that this other thing could not have happened, because they cannot happen at the same time. So for example, take a coin flip. You flip a quarter, right? If it lands on heads, that meant that it could not have been tails, right? It landing on heads means that it did not land on tails. So these events are called mutually exclusive. Landing on one side of the coin means that it could not have landed on the other side, or mean that it could not be the other one at the same time. You cannot flip a coin and it's heads and tails. It has to be heads or tails, one or the other. Now, in a situation where you have mutually exclusive events, then the probability of one of them occurring is equal to the sum of their separate probabilities. That is called the additive rule. So if I have the events of being mutually exclusive, what's the probability of this or this? I would have to add them together. So I want you to pay special attention to these symbols here, this notation that I have at the bottom here, okay? You will see the P, which means probability, and then inside you can just see letters that usually represent the event that we're talking about. So event A or B. Another way to symbolize it is A/B. Pay special attention to the slash because you may see that on an assessment where I ask you, what's the probability of A/B, for example? And you have to know slash means or, means use the additive rule. So what would you do? You would find the probability of A, and then you would find the probability of B, and you would add them together. So what's the probability of flipping a coin and it landing on heads or tails? Well, you take the probability of heads, and you take the probability of tails, and then you would add them together. Now, our next rule is called a joint probability. What's the probability of two events happening at the same time? Okay. What's the probability of two things happening at the same time? So this is when events are not mutually exclusive, and we say, okay, two events could happen together. What's the probability of them happening together? Okay. Now, one thing to keep in mind with a joint probability, and this is an important rule that I'm going to bring up in a little bit, is something called an independent event. One of the assumptions with the joint probability is that when one event happens, it's assumed that it has no effect on the other event. So, for example, if I roll a die once, and I get a 5, this has no effect on my second roll where I get a 2. So what is the probability of me rolling one die and landing on a 5, and then rolling it again and getting a 2? Well, me rolling it and getting a 5 had no effect on me rolling it again and getting a 2, right? So these events were not mutually exclusive, meaning that getting a 5 doesn't mean I couldn't have gotten a 2 the second time, right? Me getting a 5 the first time means that I didn't get anything else. It couldn't have landed on any other side of the die. But rolling it the second time, me getting a 5 didn't affect me getting a 2. So what's the probability of me rolling them together? Assuming that rolling the 5 the first time does not affect rolling the 2 the second time. Now, when you're in a situation like this, where you got independent events, and you want to know what's the probability of these independent things happening together, you would use the multiplicative rule, meaning you are going to multiply these separate probabilities together. So again, pay special attention to the notation here. What is the probability of A and B, or notated with what's the probability of A comma B? So if you see probability of something comma something, that indicates multiplicative rule. Joint probability is what's being asked for. So you find the probability of A, and then you find the probability of B, and you multiply them together. Just like I find the probability of drawing a 3, and then I find the probability of drawing a 2, and then I multiply them together, right? Or the probability of drawing a 10 or a face card, and then the probability of drawing an ace, and I multiply them together. That is a joint probability. Now, the last rule of probability I want you to know is the third and final one. There's only 3 main rules you need to know. The third is called conditional probabilities. This is where one event will occur given that some other event has occurred. So this is where probabilities are not independent from each other, that the occurrence of one has an effect on the other one occurring. So for example, what is the probability that you get into graduate school given that you've attended HCU, I need to update that. What is the probability you will get into graduate school given that you attended HCU? Okay, so the probability of getting into graduate school is conditioned upon you going to HCU, is kind of the idea here. Right? So it's the probability of one thing given that one thing happens first. Right? So given that I went to HCU, what's the probability that I get into graduate school? This is represented with the notation of the probability of A given B, or A straight line B. Right? So don't get that confused with the slash. The slash is or, P, the probability of A or B. This one, straight line, is the probability of A given B. So what is the probability of GS getting into graduate school given that you went to HBU? The given is always the second one. What's the probability of A, the first one, given the second one, whatever the second one, given that I went to HCU? Okay. Let's do some examples with conditional probabilities to help this sink in a little bit more. Okay. So let's say that I have some data that I gathered here, right? I got some information on 100 people. And I've gathered information for them about how many of them own a video game, how many of them do not own a video game, how many of them have kids, and how many of them do not have kids, and then all the combinations. How many of them own a game and have kids versus no kids? How many of them do not own a game, having kids versus not having kids, right? So I've got all those combinations there. I've got the totals, and then I've got the grand total there. So what is the probability that a person will own a video game? Well, we're not talking about owning a video game based on children. We're not even considering children. So we're just going to take the total amount of people that own a video game, right? Because that's the total number of successes that we could have. Pulling somebody out of the data set, what's the probability that I'm going to pull somebody out who owns a video game? Well, 35 people total own a video game. Out of how many? Out of 100. So we would take 35 over 100 and you get 0.35. So based on this data, I've got about a third chance of picking somebody out of the data set who owns a video game. Now, what is the probability that a person will own a video game given that they have children? Here's how you would find this. The given is what's going to kind of narrow your search when you're looking at this table here. So we're looking at having children, right? So because that's the given. We're not looking at people who don't have kids. We're only looking at people who have kids because that's our given. What's the probability of owning a game or not, versus not owning a game given the fact that you have kids? So you want to focus in on the row of children, which means that the total you're working with now is not 100 because we're not looking at everybody in the data set. We're looking at only those who have kids. And there's only 55 total people that have children. So how many of them own a video game out of the total amount that have kids? Well, that would be 25 own a video game out of the 55 people that have kids. So that's our probability fraction. And you take the division of that and you get 0.455. Okay, so you have about almost a 50% chance of pulling somebody out of the data set who owns a video game and has kids, right? Given that they have kids. So that's how you would work with the given, the conditional probabilities using a table of data like this. Let's do a few more, okay? What is the joint probability? So we're jumping back to that second rule of probability. What's the joint probability that a person will own a video game and have children, okay? Pause the video, give this one a try on your own, and let's see what you get. Okay, now that you paused the video and you gave a chance to work on it, let's see what you guys got. So what a simple thing that some of you may have done is you would have just taken how many people meet both of those conditions. How many people own a video game and have kids? Well, we see from the table, 25 people have those conditions out of how many? Out of 100, right? So I take 25 out of 100 and I get 0.25. I have a fourth chance of picking somebody who owns a video game and has kids. Now, some of you may have done it a different way. Some of you may have calculated the probability of owning a video game and then calculated the probability of having kids and then multiplied them together. And it would have looked something like this, right? 35 people out of 100 own a video game. 55 people out of 100 have kids. So 35, 0.35, 0.55, multiply them together and you get 0.19. Oh, that's two different probabilities there, right? So what do we do in that case? Which one is correct? The 25 out of 100 or taking the separate probabilities and multiplying them, okay? Now here I want to echo back to that point I made about independent events. The assumption that the events are not connected to each other, okay? When you use the multiplicative rule assumes that the events are independent. So to use the multiplicative rule, you have to assume that owning a video game is independent of having kids, that they are not connected to each other. Now, if you have reason to believe that they are connected, if you have reason to believe they're not independent, then you would take the combination number. You would take the total amount of people who own a video game and have kids out of 100. So it all depends on what is the assumption. Now, on the assessments you come across, where you have to do a probability like this, the question will specify if it's assumed that they are independent or not. So if the assumption is that they are independent, you would use the multiplicative rule, find the separate probabilities, multiply them together. If it doesn't say that they're independent, then just assume that they're related. And if you assume that they're related, then you would use the combination number out of the total, okay? Now, here's some more practice I want to give you. And I've given a new data set here. We have 162 people here, and we're looking at their political affiliation. So we've got males and females and Republican and Democrat and all the different combinations and totals there. I want you to pause the video and find all the probabilities for these different setups here on the left-hand side, right? And pay attention to the notation. This will give you practice on remembering what the symbols indicate there, okay? So hopefully you paused the video and you gave yourself some time to work these out. Let's see how well you did. What's the probability of being a Republican? Well, we're not looking at male or female. We're just looking at Republicans. So there's 70 Republicans out of 162 people total. That's 0.432. That's the probability of being a Republican in this, based on this data set. What's the joint probability of being a Republican and male? Okay. Now that, remember, I did not specify that they are independent from each other. So we're just going to take the combination number, 52 out of 162, and you get 0.321. Now, what if I had said, assume that being Republican and male are independent of each other? Well, then you would have had to take in the total amount of males and the total out of the total amount of Republicans out of the total, and then multiply their probabilities together. But since that wasn't specified, you assume they're related and use the combination number. Now, what's the probability of being Republican given that you're male? Given, which means I'm looking only at the male column. We're not looking at females for this one because we're only interested in males. So we have 79 total males. How many of them are Republican? 52. So it should be 52 out of 79. That's 0.658, okay? And then here's the results for the females, and let's see if you guys did that one right. Any that you got wrong, go back and check your results and your progress and see where you went wrong, see if you can get the right probability calculated again. Review these questions as good practice. Change up the numbers, write down this table and just change the numbers and calculate your own probabilities. This would be good practice going over these concepts, and it'll really help you refine this probabilistic type of thinking that you need for the next topics we're going to be getting into.